Thank you very much for reminding me. So what I would like to do today is I want to develop a way to calculate the acceleration of an object first intuitively, without using like any type of formula. All I want you to do is get an understanding of like, what does it mean for something to accelerate? And I think the first example, so on the sheet that I gave you, the example, it says a car accelerates from rest with a constant acceleration. Actually, I apologize. I'm going to do this a little bit today where I'm like, I have no idea what to do. I'm figuring this out. But it says a car accelerates. So can you guys see the problem now? Yeah, you can see it on my screen. Okay.
Yeah.
It says a car accelerates from rest with a constant acceleration of 2 meters per second per second. So we're going to talk about that unit again in a moment. And then it says complete the data table below. And it says draw velocity and acceleration vectors in the correct, excuse me, in the correct direction. So what I'm going to do is I'm going to do this problem on the drawing screen because it's just easier to do it on that screen than to try to figure out how to do it on this screen. So just like keep this like in mind. So I'm gonna stop that screen share and go to this one. So what I'd like to do, let's just kind of break this problem down. So the very first thing that we're told is they say from rest. Oh, that's way too pixelated. All right, so they say from rest. And what do you guys think it means for an object to accelerate, to speed up from rest? What do you think how fast do you think it's moving when it, yeah, go ahead. Who's,
yeah, me.
yeah, go ahead.
So, if you say from rest, that means that it's starting from zero or from nothing, and it wants
Very
to
good.
accelerate to a certain point.
Yeah, very good. So whenever you see from rest, it means that the velocity, and so we're going to call this, I put a little lowercase v with a little circle. We call this v naught or v initial. So like, let me write this, notation. All right, so the notation that we use is, we use these interchangeably. There is no, like, so like you'll see either v initial, v naught, or you'll see like a little v with a subscript I. I will try to be consistent, but both of these mean like initial velocity. So this means initial velocity. So like the little I here, let me do this in a different color so it doesn't seem like the same thing. So you see how that is a little I? That just stands for the first I in initial. It's your starting velocity. This little like zero, it's really a zero, but we call it V naught or V zero, it implies that time, t equals 0 seconds. So like these are used, they're like, we need to get used to using both of these notations, okay? So in this case, from rest, our initial velocity for this problem, v, and I'll try to be consistent. Like I'll just for today, I'll try to just like use v initial for initial velocity. In this case, is 0. Oh, that doesn't look like a 0. that's supposed to be a 0, guys. I'm still working on my handwriting, is 0 meters per second. Okay. Now they tell us, and I'm just going to flip back for my sake. They tell us that the car accelerates with a constant acceleration of 2 meters per second. So I'm going to write an A, a lowercase a, and I'm going to write 2 meters per second squared. So what this means, okay, in this case, we know it's speeding up. The velocity is increasing. So the velocity increases by 2 meters per second every 1 second. Can you guys still see my screen okay? Yeah?
Yep.
Okay. So what I'm trying to show you is where do these units of meters per second squared, because they at first it doesn't seem like it makes sense. So another way I'm writing this is that the velocity goes up, in this case, by 2 meters per second. Like whenever you see this little bar, okay, that's like a division sign, per 1 second. All right, so you get units of, is it a different color? This part right here, the top, is like how much the velocity in this case goes up. So we'll call this the change in velocity. And we're dividing that by what this part down here is, change in time. So remember, a change in velocity can you see that color? Let me do that a different color. So this part right here, change in velocity, the units are meter per second. And per this division sign, whenever you see it, it reads per, in this case, second. So instead of saying meters per second, we say, so spoken, it's like meters per second squared, okay? We'll get used to the units, like, but to really develop an understanding of what this all means, we really need to talk about units, and we'll do that a lot as we go. All right, so far so good?
Yes.
So check it out. So we know that, and I'm going to start making this table right next to this. All right, so we know V initial equals 0 meters per second. Now, if this velocity is increasing, so I'm going to put a little v with a subscript like 1. It's hard to see that. So that's supposed to be the number 1 second. So for the velocity after 1 second of accelerating, after 1 second of speeding up, so it's going to go from 0 meters per second. After 1 second, it'll be going 2 meters per second. After 1 more second, so I'm going to call this V2, how fast do you think it will be going? So it's going to go from 0 to 2, and then what do you
4.
think the next?
4.
Very good. So very good. 4 meters per second. How about after 1 more second? So it's like 3 seconds. What do you get?
8.
Not 8.
6.
6 meters per second. So what you should see, I'm hoping, is that, all right, this is a 1 second change in time. So the velocity went up by 2 meters per second. Between this point here and this point, the velocity increased by 2 meters per second. So this is like an increase. But we also have to take into account that it wasn't starting from rest anymore. It had an initial velocity of 2 meters per second. So we're basically going to keep, in this case, keep adding like 2 meters per second to the previous number. So every single second, the velocity goes up by 2. And then like after 1 more second, let's call this 4 seconds, what do you think the velocity will be?
8 meters per second.
Very good, 8 meters per second. So every second, the velocity increases by 2 meters per second. Does this one make sense so far?
Yes. Yeah.
Yeah?
Yeah.
All right, so now the formula that we used for this and we have a special name for this formula. It's called the first kinematic equation. Now, kinematic just means motion, okay? So kinematic just means motion. So this is the first equation of motion. And come back here. So our equation looks like this. We have our final velocity, and I'll write these terms down in a moment. That's going to equal whatever our initial velocity is plus acceleration times the change in time. So I'm going to write what these mean. So this is your, I'll do it that way. So this term here means the final velocity equals whatever the initial velocity is, your starting velocity, plus the acceleration times the change in time. For this one, I'm just going to write acceleration that's supposed to be times the change in time. And just for one last thing, this part right here represents how much the velocity changes. So this is how much the velocity, so this little part here. So like sometimes we say it's how much the velocity changes, so increases or decreases. So in this case, in this example, we did one where the velocity increases. So how much the velocity increases, or it could decrease, if it was slowing down. All right. Does this one make sense so far?
Yes.
So I'm gonna show you how to use this formula. And if you guys could tell me, I don't want to go too fast. So if you're still writing, please just write, and I'll slow down a bit.
I think it's fine, especially if after the meeting you can give us the recording, we can just go over it again.
Absolutely. And it will take I'll upload this later tonight because I have a class right after our own class today. So like I'll upload it hopefully by tonight. If
Okay.
not tonight, definitely by tomorrow morning. Now, on that problem sheet, so we figured out the velocity like after 1 second, 2 seconds, 3 seconds, and 4. But on the the right-hand side, it also asks you to figure out the velocity after 0.5 seconds, 1.75 seconds, and so on. So what I'd like to do is show you how to find the velocity after 0.5 seconds. And this is why you want like an actual formula and not this is why, like the intuitive method doesn't work very well when when the time differences get different or change. So what we want to know, we want to know the velocity. And actually what I'm going to do for this, well, actually, do you know what? Let's say a velocity after, or I shouldn't say after, I should say at. What was that? Velocity is, what time, what did I say for time? Half a second? Okay. So velocity for t equals 0.5 seconds. So this is what we're gonna try to find the velocity when t equals 0.5 seconds. So to do that, you're like, this is a good practice. Always write down the formula that you're using. So we know that v final, the final velocity, the velocity after half of a second, equals whatever the initial velocity is plus the acceleration times the change in time. So the information that we plug in, so our final velocity is our unknown. Now our initial velocity, that's the starting velocity, is 0 meters per second. Now we're going to add to that the acceleration, which we know the acceleration is 2 meters per second squared, and put some parentheses around that. And the change in time, how much the time has increased from 0 seconds to 0.5 seconds, is going to be just 0.5 seconds. Now, a couple of things that I do want to highlight here. You see this unit of second squared? So there's a unit of a second squared here. All right. That's going to cancel one of the units of seconds here. So the way we usually write this, and do that in blue. So this unit squared cancels with this second. And what you're going to be left with is, so I'm just going to do this again, v final equals 0. 2 times 0.5 is the number 1. And then your units, so like 2 times 0.5, 2 times 1/2 is what I'm looking at, will be 1 meter per second. That's it, not meters per second squared, but just meters per second. And that's going to be the velocity that you're looking for after half of a second. Now, here's what I would like you to do. There's the next one on there. You need to find the velocity after 1.75 seconds. So what I'd like you to do, so let's draw a line through here. I'd like you to find the velocity. We'll call it v final. Sorry, let me use a different color for that. So can you find the v final? when t equals, is it 1.75 seconds? I think that's what I wrote. So what I'd like you to do is use this formula, and I'd like you to correctly identify your variables. I'm going to give you a hint though, just to help you get started. This value right here, this V initial, that's going to be 0 meters per second. So this number here is, you've started at rest and now you've sped up. All right. So remember, this V initial is going to be 0 meters per second. Okay. You're starting from rest. And what I'd like you to do is find the correct values to put into the other two variables. I'll give you guys a minute to do that. Can one of you tell me what 2 times 1.75 is?
3.5.
Very good. So 3.5 meters per second. Okay. Do you guys have a question on this problem? Yeah, no? All right,
No.
cool. What I would like to do is, and I think it's, I'm gonna stop screen sharing for 1 second. Well, I'm gonna switch the screens. All right, so what I'd like to do is look, oh, why is nothing on that? I don't know why there's a page blank there, but okay. I'm gonna skip number 2, and I think I have a problem. Well, why is that not there? All right, I don't know why it, okay, it's actually missing several problems. I don't know why. So I'm gonna, I wanna show you an example of a different problem. So what I'm gonna do is I'm just gonna clear this screen. Does anyone need that still? Do you guys need that? No? Okay, so check it out. I'm gonna just clear the screen. Hang on a second while I figure out how to do that. Hopefully I'm doing it right. Can't tell anymore. So what I want to do is I want to try to help you think about how to figure out the velocity if something is slowing down. And so I'm going to make up a problem, like a sample problem. So I'm going to give you a different initial velocity. So imagine you have like a car, and the initial velocity of the car is, let's say, 12 meters per second. And I'm going to tell you that it's slowing down. So it's, go back for a second here. So it's going to slowing down at a rate of, let's say, 4 meters per second or meters per second squared. What I'd like to do is just intuitively figure out what is the velocity after slowing down for 1 second, 2 seconds, and 3 seconds. Before we do that, though, what I would like to also do in addition I would like to draw velocity and acceleration vectors. So, why did I do that? Sorry, guys. I'm just trying to figure this screen out. So is the velocity positive or negative? What do you guys think?
Negative.
Yeah. No, in this case, so like, unless, if whatever the sign of this number is, the velocity, if it's positive, if it's a positive number, it means it's going in the positive direction. So like, do you know how like any number can be written as like, in this case, I could say plus 12 meters per second, but that's the same thing as just saying 12. We don't usually put the positive sign here. But if it's a negative velocity, we must put the negative here, okay? So our velocity vector, try to draw that a little straighter. Our velocity vector would point in this direction, okay? And why is it this direction? Because like, if you think of like a number line, so like if this is not a vector, but if you think of like a number line with 0 here, anything this direction we usually say is the positive. Anything this direction is like the negative. It's like just like the number line, typical number line. And so like this is usually the positive direction. Now in this case though, it says the car is slowing down at a rate of 4 meters per second squared. What was that rule that we had? We talked about, I think it was last time. What direction do the vectors have to point for something slowing down? Same direction or opposite direction?
Opposite directions.
Yeah, very good. So like this is slowing down. So they're going to point in opposite directions. So like whenever you see like vectors pointing in opposite, like motion vectors, whenever you see velocity and acceleration point in opposite directions means slowing down. Now here's the trick though. Well, actually, let's first do this intuitively. Back in yellow. All right, so we know that the initial velocity, I'm going to write it as V initial, VI, equals 12 meters per second. And we know it's slowing down. So should we get a bigger number or a smaller number? What do you think? After 1
Smaller.
second of slowing. Yeah, so what do you think the velocity is after 1 second of slowing down? How much does the velocity change by?
Oh, 4 meters per second.
Yeah, so it's going to decrease. So it's going to go from 12 to what's this number here?
8. 8.
Very good, 8 meters per second. And after 1 more second, so after 2 seconds in total, what should the new velocity be?
4.
Anyone can yell it. Yeah, very good, 4 meters per second. And after 1 more second, what should the velocity be?
2.
0.
Very good.
Oh, 0.
Now let me ask you, yeah, 0. And let me ask you a question. If it's slowing down, right, it's coming to a stop, right? If it's slowing down, it's coming to a stop. We're going to assume for this problem, it's not going to continue to accelerate. It's just going to come to a stop. Now, don't know why that did that.
So I have one question.
Yeah, go ahead.
So here on my notebook, I don't know if you can see well, just this thing on top here. Don't mind it, but would that be correct?
Hang on 1 second. I'm going to try to make your screen bigger so I can. Okay, that better. Go down a little bit. Yeah, so that's what I'm about to show you, Ryan. That's what I'm going to show you is the one thing that we left out is the negative sign. Very good. That's what I was hoping you would see, guys. So yeah, very good. Good work. So what I was going to show you here is that the difference between these two, like any 2 points, is the velocity goes down by 4 meters per second every second. So between those two, between these two, minus 4 meters per second squared, every second, because this is slowing down, it decreases by 4 meters per second. Now, the reason is it okay if I go up a little on the screen? So for this case, when you see something that says slowing down, okay, you have to go and put the sign of the velocity in. So, sorry, the sign of the acceleration in. Let me just fix this screen. So very good, Ryan. Now, how we would write that, so do this in green. So, just continuing here, like we know that the initial velocity was 12 meters per second. Now, how we write the acceleration, so lowercase a, and we know it's 4 meters per second squared. We know that's how big it is, the magnitude. But what we have to do is write minus 4 meters per second squared. And this is why we actually draw the vectors, to determine this sign, to know if this is let me do a different color for that. To know what sign the acceleration is, we have to look at the acceleration, or we have to look at these vectors, okay? Use vectors. So use vectors to determine if this is a positive number or a negative number. So in this case, like you see, we have the velocity vector pointing in the positive direction. The acceleration vector points in the opposite way. So that's like the negative direction. So what I want to do is, okay, we have about 5 minutes. I just want to do one more continuation of this problem with you. So let's figure out, what I would like you to do is use this information. Can you guys figure out the final velocity after, so assume we know what the initial velocity is. When t equals let's say 2.25 seconds. Can you use our kinematic equation to figure out the velocity? So go ahead and try to figure out that velocity after 2.25 seconds. All right, did everyone get 3 meters per second?
Yes.
Yep.
Yeah.
Yeah, and the thing I just want to point out is we write the parentheses around the 4 meters per second because we have to be careful of that negative sign. We have to make sure that we think about the problem and find the negative, or find whether it's positive or negative before we do anything. And just to check ourselves, so what do we say? This is after 2.25 seconds. So we know that 2.25 seconds is like, so right around here. Let me do that a different color. So like V, that's a terrible, V at 2.25 seconds is somewhere between 4 and 0 meters per second. And, you know, we figured out that it was 3 meters per second. So we know that we haven't made just a simple mistake. If we were to get a number that wasn't between those two numbers, we know we would be making a mistake. All right. For homework, what I would like you to do is just finish this sheet right here. So there's like 2 problems. There's no calculation for the left-hand side. All right, there's no calculations for this side. And, you know, it's just like you use your intuition. And the same over here, like the bottom side, you're just using your intuition and then just try to figure out the velocity. And so there's 1, 2, 3, 4, 5, 6, 7. I don't want you to do 7, like don't do this for 7 times. All I would like you to do is choose 3 points on here. Just choose 3 of these times to calculate the velocity. That's all. I'm not going to make you do it 7 times. Just do it like choose 3 and just make sure that you do it correctly. Okay. Do you guys have any questions on any of these problems or what I'm asking you to do for homework?
No.
All right. Well, with that said, then, hang on one second. So,